Hey folks, NMR Chemist here, and today I am going to show you how to interpret an NMR spectrum. And this particular spectrum is that of an alcohol, and it's called cinnamyl alcohol, and the structure of it is right over here. So, now, the thing I'm going to show you how to do is how to assign the signals in this spectrum to the protons on this structure. No. Oh, file history, go away, please. Thanks. Okay, so the first thing I typically do is I scan the spectrum for a few different areas. First area I'll look for is in the aromatic area, which is about 7. Let's see, I have my notes over here. Yeah, the aromatic's usually around 7 to 8.5 ppm. So the first thing I'll do is look over here, and yes, we do indeed have an aromatic region. And then I also see this molecule has an alkene area. So I'll look around the entire spectrum and see, is there any protons in the alkene area? And well, yeah, this looks like the area where you might find alkene, 5.5 to 6.5-ish ppm. But I also see there's two other types of protons here. There's the OH proton here, and there's two protons right here, which are alkyl group. So, what I will look for next is for the alkyl region. And yeah, this is definitely where I would expect to find alkyl protons. And this over here is where a decent spot where you could find an OH proton. The OH proton can literally be anywhere between 0.5 and 5, depending on the specific compound you're looking at. Carboxylic acids are usually around 10, by the way. This peak over here is tetramethylsilane, which happens to be in the spatulochloroform, and that's the internal standard relative to which all NMR samples are taken. Well, proton anyway, and carbon too. So, now, another thing is you may be asking is, but wait, Mr. Chemist, how did you know that these signals correspond to these protons? Well, I am about to assign the signals you see in this NMR spectrum to the protons on the molecule. The first thing you need to know is that every single peak you see in this spectrum corresponds to one unique proton environment. There could be more than one proton in that environment, though. For example, this methylene group would have 2. I'll tell you how I got to that in a moment. But you can tell how many protons are in a given environment by these numbers right down here, which is the area of the peaks. And this one integrated kind of funny, some reason. It integrated 1.5-ish, but the OH integration area can be a little off sometimes, as can NH protons. But let's see, we have 2 here, 1 here, 1 here, 1 over here, 2 here, and 2 here. So that gives us 2, 4, 5, 6, 7, 8, 9, 10. 10 protons. Let's count around the molecule. 1, 2, 3, 4, 5, 6, 7, 8, 9. Did I miscount that? I feel like I miscounted. 2, 4, 5, 6, 7, 8, 9, 10. Yes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. There are 10 protons. This totally makes sense. So, sorry, I'm looking at my notes on the other computer over here. You might be asking yourself, well, what does all this splitting mean? Like, I see a doublet here. I see a doublet over here. Triplet here. And what the heck is this complicated pattern over here? Well, here's how splitting works. It has to do with the number of hydrogens on neighboring carbons. For example, in this molecule here, these two protons here are split into a doublet by the proton on this carbon right here. Okay? They are not split by the protons on oxygens or nitrogens in general. In some occasions, you'll have multiple signals overlapping, and then you'll get a multiple like we have over here. But in general, the number of neighboring hydrogens relative to the one that produced that peak is given by the n+1 rule. So, if you have a doublet, it means that this hydrogen has one neighbor, a triplet means it has two, quartet means three, and so on and so forth. So, but then you might be asking, well, wait, what kind of fancy signal do we have going on over here? Well, this signal here is, it's a doublet of triplets. This arises because it's different coupling constants between neighboring protons. And basically what happened here was the signal from this proton was split into a doublet by this proton over here. But then this doublet here was split again into a triplet by these two protons here. Sorry, each peak in the doublet was split into a triplet by the two protons over here. So that's how you get a doublet of triplets. And this will happen anytime you have two protons with sufficiently different coupling constants. Okay, what are coupling constants? The coupling constants are the distance between two peaks, for example, this one and this one. For this alkene here, the coupling constant is about 15.9 hertz. Please go away, ruler. And for the for this methylene group, this is the methylene group, by the way, the coupling constant would be 5.6 hertz. Okay, seems about right. Now, and if we go over to our fancy doublet of triplets, which is located right over here, we have two different coupling constants. The first one is 15.9 hertz. Does that sound familiar to you? Well, yes, it should, because the coupling constant for this proton right over here with this one should be the same if they truly are coupled. Discord, go away, please. And then, if we measure this coupling constant over here, we should have around 5.6, 5.7 hertz, and yes, we do indeed get that, because this proton is coupled with these two, and they should have the same coupling constant. Another thing you may have noticed if you were observant is, but wait, this looks like a doublet of doublets. What's going on over here? Well, actually, what's going on here is that you're getting some long-range coupling here, which is usually indicative. It usually occurs if you have a, or a sign of that is if you have a really small coupling constant. Like this one's only 1.1 hertz. What's happening in this case is these two protons are coupled to this one over here, but they're also weakly coupled to this one down here, which is farther away than normal, so you get a much weaker coupling than you would normally expect to see. Now, the coupling constant you saw here was 1.1 Hertz. You might be asking, well, why aren't I seeing any long-range coupling over here? Well, because the spectrometer, a 300 megahertz spectrometer, is probably not powerful enough to completely resolve this. But if you look really carefully at these peaks, you can see that it is trying to form a doublet of triplets. And look at that. If we look at where these very weak shoulders are at, we get a value around 1.1, 1.2 Hertz. So, yep, that's the long-range coupling again. So, let's see. And one final thing you may have noticed while looking at these peaks is the tilt. These peaks appear to be leaning against these peaks. And that, again, tells you that this group is coupled with this group, because if peaks are coupled, they will often, not always, lean towards one another. In general, if you see two peaks leaning towards one another, there's a good chance they might be coupled. Now, let's finish this proton assignment, shall we? Let's start in the aromatic ring, because that's probably the easiest region, I guess. Well, it's probably not, but I like to work from left to right with these spectra. So, let's focus on this peak over here first. We have an area of 2, and it's split into a doublet. Now, what could possibly give us that in our structure? Well, we have 2 protons, and they only have one neighbor. So that would be these 2 orthoprotons right here. And if we move over to the peak around 7.25 ppm, there's a triplet here with an area of 2. Now what could that possibly be? Well, where there are 2 protons in this molecule that have 2 neighbors, well, there's only one spot. It's these metaprotons over here. Then, our last proton here has to be the para, which would ideally be a triplet, but for some reason, probably because of long-range coupling, you can see a little bit of the long-range coupling occurring over here because these peaks aren't entirely sharp. This got split up into a multiplet, but with an area of 1, it means there's only one proton, and it can only be this one here, based on its chemical shift. Alkene protons are almost never found in the region of 7.15 ppm. So, now we've got the aromatic region squared away. Let's head over to the alkene area. Now, what could possibly be giving us this signal here? Well, we've got ourselves a doublet, and it has a very large coupling constant of actually close to 16 Hertz. If you see a coupling constant of 16 Hertz, you can almost bet that you're dealing with an alkene. And because it's a doublet with an area of 1, we are looking for one hydrogen in an alkene that has one neighbor, and, well, this one right here would be a good choice, wouldn't it? I think so. So what about this fancy doublet of triplets that we're seeing over here? What can possibly give us that? Well, we're looking for 2 different things here. There's one proton here, and it is being split by one proton that is probably an alkene proton based on this really big coupling constant. And it's when that signal is being split again by some alkyl group protons, according to this small coupling constant. So they're about 5.7 hertz, if I remember correctly. Let's measure that to be sure. Yeah, it's 5.79 hertz. So, which proton in this molecule can give us that? Well, I would say this one here, because it's going to be split into a doublet by this alkene proton. That doublet will be split into two triplets by these two protons on the methylene group. And there's only one proton giving us this signal. So what's left? A couple more signals. How about this one here? Well, this is a doublet with some long-range coupling based on this really small coupling constant. So we're looking, it's got two protons giving us the signal, and it's in the alkyl region. So we're in our molecule over here. Can we find that? Well, I'd say over here, because here we have one neighbor, two protons, and so we should get a doublet in an area of 2, and that's what we have here, indeed. Coupling constant is 5.7 hertz, and that's pretty reasonable for an sp3 hybridized carbon. The last peak we can find in this structure, spectrum I mean, is this one over here. And because this is a singlet, this can only be one thing. It has to be the OH proton, because there's no other protons left in this. One other thing I should also mention is the coupling constant of these aromatic protons will typically be approximately 7 hertz or so. Could be up to 8 hertz. Really depends on your structure. So, there you have it, folks. This is how I interpreted the NMR of cinnamyl alcohol, which, coincidentally, is one of my favorite chemical compounds of all time. Did you think this was good? If yes, please leave a like on the video, as I would definitely appreciate it. But anyways, I'm NS Eastern Shore Chemist, and I'm signing off. Thanks a lot for watching.